The objectives of this video are the following. First, I'd like for you to be able to explain the main trends in successive ionization energy data. So I'd give you a graph like that, and I'd want you to be able to tell me or explain to me what is going on there. Why are there these jumps, and why does it seem to trend upwards? Secondly, I'd like for you to be able to look at a graph like that and deduce the group of the element whose data that is. Okay? Thirdly, I'd like for you to be able to explain the trends in first ionization energy across periods 2 and 3. So you'd be able to look at a graph like that and explain the pattern that you see. So let's get started. The first thing is to explain, of course, the trends in ionization energy, or rather to explain the successive ionization energy data for specific elements. Let's start with a general definition of ionization energy. I think I've already given this to you before, but we'll go through it anyways. Ionization energy we define as the energy needed to remove an electron from an atom in the gaseous state. So you take an atom and you remove an electron, and you've ionized that atom, okay? We usually standardize it in the gaseous state because it would be slightly different in a liquid or in a solid state. Here's an example here. We have a hydrogen atom, we add some amount of energy to it, and the energy we add is able to knock out this electron, and so we have a lone electron and a proton there, or a positive ion, okay? Now hydrogen has just one electron, but for multi-electron atoms, for atoms with many electrons, we can test how difficult it is to remove each successive electron. So take aluminium here. Aluminium has 13 electrons. We can see how much energy do we need to take out just this first electron here. Okay, we call that ionization energy 1, or first ionization energy. And then we can see then, how about the next electron? So we take this ion here, the monopositive ion, and try to knock out another electron from it with some amount of energy, and that energy would be called the second ionization energy, and so on. How do we do this process of measuring the amount of ionization energy required to knock out electrons? The IB doesn't really care that you know, but I'll go through it anyways very quickly. So this is an extension. The idea simply is that you would take your sample. Here we have aluminium. You need to vaporize it because remember we measure this in the gaseous state. So you vaporize it and you put it in some kind of chamber, and you're going to expose that chamber to light whose frequency or energy you can modulate. Okay? So here's the idea, is we're going to raise the frequency of this light gradually. Remember that frequency correlates with energy for light. So we raise the frequency of the light gradually until we're able to knock out a set of electrons from our billions of aluminum atoms. And we can measure at what specific frequency were those electrons emitted. Okay, obviously we won't be able to see this picture. This is a theorist's picture, but we can measure actually when it is that electrons are released. And so we note that energy as the first ionization energy. We raise it again. Okay, so like I said, we note it, and then we raise the energy again until we can knock out another set of electrons. And we note that energy as the second ionization energy. And we just repeat this process on and on. When we do this, we get a graph, and it's this graph that the IB wants you to know. So we can put on the x-axis the number of the electron that was removed. So the first electron, how much energy did it require to remove? The second one, the third one, and so on. On the y-axis, we put the ionization energy, but we log transform it. Log transform basically helps us take a graph that expands too far vertically and squeeze it down. Hopefully you understand what log does to numbers. So let's see what the trend is. We start with the first electron. That's the easiest to remove. Then it's slightly harder, then slightly harder again. And then we have a jump. There's a jump between electrons 3 and 4. And then we slightly harder again, and so on. And then we have another jump there between electrons 11 and 12. Okay? So it seems like there's this sort of, there were 3 where it was going up gradually, then we had a jump, and then we had 8 where it was going up gradually, and then another jump. How do we explain this pattern, this trend? Well, if we remember just the main level configuration of aluminium, it should be obvious, right? Because here we have 3 in the outermost shell, 3 electrons, so those would go out first. And then we have 8 in the next shell, so there, and then 2 in the innermost shell, or energy level. Shell and energy level are synonyms. So it looks like we can identify 2 main patterns, or 2 main observations. The first is that ionization energy seems to increase gradually as electrons are removed from the same shell. So here's the first shell, or actually the third shell, the outermost shell. It seems to be increasing gradually as we take out each electron. Okay. Then there seems to be this jump, this large jump in ionization energy between the shells. And then after the jump, then we resume the gradual slope. So how do we explain these trends? Let's look at the first one. Ionization energy increases gradually as electrons are removed from the same energy level. Why is this the case? Here's the reason. As electrons are removed, we end up with what? Reduced repulsion. And the reduced repulsion allows the remaining electrons to get closer to the nucleus, where they are held more strongly. What does that mean? So here we have 8 electrons. As we remove electrons, you know that electrons, like charges, repel, right? So as electrons are repelling each other, they're forcing basically this ring, or this, you can think this electron cloud, to be bigger. And as you remove them, then the electron cloud is allowed to constrict because you have less electron-electron repulsion. Here's an analogy. You're playing some game on a field, and you and your friends have to basically make a circle in which you must stand arms width apart. So you must stand arms width apart, and that arms width apart standing form is basically an analogy for the repulsion. How can we make this circle smaller? Well, we can just remove people from the circle. When you remove people, then we have less repulsion, less arm width, and we can reduce then the circumference of the circle. Similar case with the electrons. As we remove electrons, we reduce the repulsion, and therefore we allow the electrons to come closer to the nucleus. When electrons are closer to the nucleus, they're held more strongly, therefore they're harder to remove. Okay? So if we take this shell, for example, when we go from 8 electrons in there to 7, then the ring is slightly smaller, and therefore they're harder to remove. And then here we go to 6, and the ring gets smaller still, and harder still to remove. I'm using the word ring, but remember, electrons don't exist on rings around nuclei. That was the old belief. Now we subscribe to the theory of orbitals, but we still use rings anyways because it's easy and it explains much of what we need to explain. Let's look at the next trend, this large jump in ionization energy between different energy levels. So from here to here and from there to there. How do we explain this? There are 2 main explanations. They're kind of similar ways of saying the same thing, but you might be tested on them separately. So this first one says, electrons in a lower shell are significantly closer to the nucleus. This is extremely obvious, right? If we take these dark blue electrons here, they're closer to that pole of the nucleus, those positive charges, and therefore they're going to be held more strongly. So that's very obvious. The second one says there's less shielding for electrons in a lower shell. So they're exposed to a higher effective nuclear charge. What does that mean? Consider this pink electron here. Well, actually, consider the dark ones first. What is the charge that they're exposed to? They're going to be exposed to the full 13 plus charge in this aluminum nucleus. Okay, there are 13 protons in there. That's what makes it aluminum. So they're exposed to the full charge. But this guy out here on the shell outside, he's not going to be exposed to the full charge. These guys moving around are going to block some of that charge. That's what we call electron shielding. So you end up with the positive charge in the middle, and there's these negative charge stuff blocking some of the charge for this electron. So this electron here on the outside doesn't see that full charge. Here's an analogy that might help. So first of all, we have here 2 concentric circles of people holding hands. Imagine now we opened up a portal in the ground that was sucking air in, trying to pull these poor fellas into the ground. We would imagine that the folks on the outside, the orange, would feel a less strong force for 2 reasons. First, they're further away and therefore the force is less strong. That's this one. But secondly, because the folks in the middle here are blocking some of the pulling force, blocking some of the wind, some of that gust. And therefore, they shield the outer electrons, or they're the outer people, from that, from the pull of the wind, or back to atoms from the nuclear charge. So the effective nuclear charge for the outer electrons is reduced. For the inner electrons, it's higher. Okay? So that explains these jumps, those two trends. Hopefully that makes some sense. So we've identified two trends now, but if we look a little bit deeper, there's this sort of other subtrend or sub-pattern that we might notice. Let's zoom into these first three. We can see that there seems to be a sort of steeper slope between these and then a milder slope there between electrons 2 and 3. Why is it that 2 is so much harder than 1 and 3 is not that much harder to remove than 2? To explain this, we look at the sub-level diagram. So here we've just been looking at the main level diagram, but we need to look at the sub-levels to understand what's going on here. Here's the idea. To remove this first electron, that first electron happens to be a 3p electron. By now you should be able to write from memory the electronic configuration of aluminum just by looking at a periodic table. So this should be coming naturally to you. Hopefully you remember this. Anyways, so we have that 3p electron, and that one is higher energy and easier to remove than this next set in the what I've colored yellow orbital. Therefore, this is easier to remove than this next set. So we have an additional effect of the different orbitals there. Now, not the different orbitals, the different sublevels. So here it is again in brief. We say that this electron is in a sublevel which is slightly higher energy, less stable, easier to remove, while these next two are slightly lower energy, more stable, and therefore harder to remove. If you want an analogy, here's one for you. We have these three electrons, they're in the same shell, so kind of they're in the same ring holding hands, but one of them is higher energy, one of them is a child, and the other two are lower energy. They're Galapagos tortoises, and therefore harder to remove, harder to pull out of that circle. Okay? Therefore, these two are harder to pull out than this one. Okay? Hopefully that makes sense. All right. Therefore, we can add now this one, this third subtrend that I mentioned, the smaller jump between electron sublevels or subshells. If we zoom into the next 8, we can also see a similar thing. Between these first 6 and the next 2, there seems to be a kind of jump. Okay? And if we look at the sublevels here, between basically these 6 electrons removed from the 2p, those ones seem to be easier than the next sublevel in the 2s. I've been talking a lot. Let's see if we can give some kind of a summary. So we've gone through this diagram and we're trying to explain the trends. This, remember, is the successive ionization energy data for aluminum. And we said that if you look at either this picture or that picture, you can get a sense of what is going on here. We identified 3 different trends. The first is a gradual increase in ionization energy across the same energy level. Okay? And we explained that by reference to the reduced electron repulsion as we take out electrons, as illustrated by that picture there. Secondly, we discussed large jumps between different energy levels here and here. This is just for aluminum. We'll look at some other ones in a second. But we talked about these large jumps, and we explained those by reference both to the fact that we move to a closer shell, a shell that's closer to the nucleus, and secondly, the fact that the lower shells basically shield the outer shells, and therefore the outer shells are exposed to a lower effective nuclear charge. And there's your picture there if you need that. And finally, we talked about the smaller jumps between subshells because the lower subshells are a bit more stable, it says, and therefore harder to remove. And we have that picture there to help you with that. So what kind of question might you get on the exam about this? You might get a question to do exactly what we've just done here. Explain the trends that you see on some successive ionization energy data graph. So they might say, here's a graph of the successive ionization energies of aluminum. Please explain for me the general rise in ionization energy, the discontinuity between electron 3 and 4, and the discontinuity between electron 11 and 12. And how would you do that? You would go over what I just said. Here it is in prose form in a way that you could write down. And I would recommend, if you were to do this, to draw the simple main energy level structure of the atom you are asked to analyze. In that case, aluminum. So if you want, you can pause and write this down, or just pause to read through it and process it. Okay? But if you're already good with it, we're going to move through it. I think we're done now with this first objective. My pen is quite what's the adjective for misbehavior? It's full of mischief today. Okay, secondly, we'd like to deduce the group of an element from data on its successive ionization energies. So how do we do that? Let's look now, for example, at this picture. It says a graph of the successive ionization energies of an element is shown. What group does this element belong to? How do we make such a decision? How do we figure out what group this element belongs to? It's really quite simple. We need to count the number of electrons before we have a jump. Here we have 3 electrons before a jump. That means there are 3 electrons on the outside that is easy to remove. There are 3 valence electrons. And the number of valence electrons we know tells us the group. So the number of electrons before a jump tells us the valence electrons, which tells us the group. I didn't include the valence stuff here. Hopefully you know how to spell the word valence by now. It tells us the valence electrons, which tells us the group. But one thing to note is that if one valence electron matches to group 1, 2 valence electrons group 2, 3 is group 13. Hopefully you remember that, because for most of these questions they'll tend to ask you for the first 20 elements. So let's shrink this periodic table to the first 20 elements. We squeeze that in, okay? And then let's now represent the full electronic configurations, or rather the main level configurations for these first 20. And now we can observe what I was saying, that for 1 valence shell electron here, that's group 1, 2, group 2, 3, group 13. Why? Because we had that jump where we cut out the D block. Okay, so hopefully from here now it is clear that the number of valence electrons would give you the group. And the number of valence electrons we can get from the successive ionization energy data. That is what I just said, so I'll skip through it. Let's try this question. Pause the video and read it and see if you can give it a go. It says, the diagram above shows the first 10 ionization energies for an element. Let's call that element X. Which of these could be the element? Again, pause the video, try to work through it. Which of these could be the element? In 3 seconds, I will show you now a clue. 1, 2, 3. Here's our clue. It's just our periodic table. And then 1, 2, 3, I show you the answer. Here's the answer. Answer A. Why is it A? Well, let's see. There's 6 electrons, or 6 electrons were removed before we had that jump. It means there must be 6 valence electrons. Which group has 6 valence electrons? Group 16. So either we're talking about oxygen or we're talking about sulfur. So which one is it? It can't be oxygen. Why? Because oxygen has only 8 electrons. And here we're talking about removing 10 electrons. It shows the first 10 ionization energies. So it has to therefore be sulfur. Let's move to another one. Sketch a graph of the first 4 ionization energies for magnesium. How would you go about doing this? Pause, think about it, see if you can sketch something on whatever piece of paper you have around you. And in 3 seconds, I will reveal the solution. 1, 2, and a 3. Here is our solution, okay? So, since it's magnesium here, it's in group 2, there are 2 valence electrons, therefore they're going to be 2 relatively easy ones to remove. And then we jump up because we move into the next main shell or energy level, an N of 2, right? N equals 2. This is the next level. And those 2 will be harder to remove, therefore we jump up that way, okay? And make sure you get the slight slope between these first 2, because as we're removing electrons, reduced electron repulsion allows the electrons to come closer to the nucleus, and it makes it harder to pull them off. Here's another one for you. Again, pause the video, read through it, see if you can get it right. It says the table above shows the first 4 ionization, well, there should be 6, the first 6 ionization energies for an element X. Deduce the group of the element. How do we do this? This looks unfamiliar, but just think about the fact that this might as well, or could have been a graph, right? Here's the idea. We have how many values, how many ionization energies before we have a jump. Here we go from 600 roughly to 1800 roughly to 2700 roughly, okay? And then we jump to 12,000 more or less. So there we have a big jump, which means we have 3 valence shell electrons before it gets hard, which means we must be indeed in group 13. Okay, and 13 is indeed there. So our answer is C. Beautiful, beautiful. We're done with number 2. Wow, we're going so fast. Number 3, I can explain the trends in first ionization energy across periods 2 and 3. How do we explain such a graph? Let's do a revision of our definitions. We remember the definition of ionization energy as the energy needed to remove an electron from an atom in the gaseous state. We can be more specific and define what we call the first ionization energy. You might be asked for this definition on the exam. The first ionization energy is the energy needed to remove the first or the most loosely held electron, the most loosely bound electron, from a neutral atom, it says there, in the gaseous state. So let's look at an example. Here we have lithium. Lithium is neutral. Okay, why must it be neutral? Because if you haven't taken any electrons away from it, then it must still be neutral. It must have the same number of protons as it does electrons. So now we go from lithium and we add some amount of energy. We're able to knock out that electron and we create a lithium monopositive ion. What we can do is we can measure across a period to see, does this ionization energy, this first ionization energy, does it get easier or harder, or lower or lower or higher? Okay, that is if we take the most loosely held electron here in beryllium, is it going to be easier or harder to remove than the most loosely held electron here? And then we try it again with boron on across. To explain the trend we're going to see, we're going to need to refer to the sublevel and orbital level diagrams. Okay, so we get rid of that picture for now. We focus on this one. Here is the trend. It's really quite a simple trend. The trend goes generally upwards, so it's easier to remove the first or most loosely held electron from lithium than it is for beryllium. So beryllium is easier to remove, but then we have a dip to boron, and then it gets, beryllium is harder to remove, so it's getting harder, and then we get a dip, and it's easier for boron, and it gets harder again, and then easier for oxygen, and then harder again, and harder again. So it seems we have this sort of dog tooth pattern, or I don't know how you would describe the shape, but it's generally going up with two discontinuities. How do we explain all of this? First of all, let's name the trends. We name first an overall upward trend, and discontinuities between beryllium and boron and nitrogen and oxygen. The overall upward trend we explain by reference to the nuclear charge. The nuclear charge is growing across this period, so the electrons are going to be held more tightly. Secondly, the radius is decreasing, so the electrons are held more closely. Both of those are kind of obvious, but let's still give a quick analogy for that. So imagine now that the nucleus is a positively charged thing, and it's pulling the electrons in, those negatively charged electrons, right? So imagine the nucleus as a vacuum which is holding in these dollar bills. Okay, so your vacuum is on and pulling these dollar bills close to it. And these dollar bills, which are clogging the vacuum, are our electrons. So what's happening here is, as the number of protons is going up, the pull of the pull of the positive charge is increasing. And similarly here, the level that you set the vacuum on is increasing. Because that's happening, you can imagine it gets harder to pull out one of these dollar bills. Therefore, it's getting harder to pull out one of the electrons across the period. So as the positive charge increases, it gets harder to release an electron. Similarly, so we explain this part, for the radius, you can imagine that the dollar bills crumple more tightly as we increase the power of this vacuum, and therefore it's harder to kind of get a grip and pull them out. Okay, so the electron cloud is shrinking as we go across the group. It's harder to pull those out. Again, these are two ways kind of saying the same thing, but sometimes you might be tested on them separately. Let's move on to the discontinuities. What is this discontinuity about, the beryllium to boron? To explain it, we need to look at this sublevel diagram, or this orbital diagram. What it says there is that the most loosely held electron for boron is in a 2p orbital, while it is in a 2s orbital for beryllium. Okay, and 2p is higher in energy and more stable and less stable than the 2s. You can see here I've drawn the 2p as higher energy than the 2s, which means it's easier to remove. High energy translates to easier to remove. You can think it's moving around the nucleus real quick, and therefore we can just kind of flick it out and it'll go flying out of the nucleus. Here's a diagram of those atoms. So here's beryllium here. We have just only s electrons, right? So we have these two, the 1s electrons in the small sphere and the 2s in the larger sphere. When we go to boron, though, we need to add in that p shell. And for some weird quantum mechanical reasons, sorry, not p shell, p orbital. For some weird quantum mechanical reasons, the p orbital is higher energy than the s orbital. Therefore, it's easier to remove. If you want an analogy, you can think again of our tortoises. The tortoises are the s electrons, and the child is the p electron. So boron has one child, so one p electron, and 2 tortoises. So it's going to be easy to pull out that child. Therefore, it's easier to pull out the electron from boron. But beryllium only has these 2 tortoises. It's harder to pull out that electron because the tortoises are lower energy, more stable, harder to remove. The second one, between nitrogen and oxygen. The reason here is that in oxygen, the most loosely held electron is in a paired orbital, and therefore it experiences repulsion from the other electrons. Electrons don't like each other, so when you put them together in an orbital, they repel against each other, and therefore they're easier to pull out. Okay, it's easier to remove electrons from a paired orbital than it is to remove them from a singly occupied orbital. If you want pictures now, let's see pictures of nitrogen and oxygen. Here's nitrogen's structure here. You can see that in each of these p orbitals, we only have 1 electron. So 1 electron in the px, 1 electron in the py, 1 electron in the pz, which goes in and out of the board. If we look at oxygen, we can see that we have 2 electrons in this px now. Those electrons repel each other, and it's easy to remove one of them. Okay, a possible exam question. The diagram shows the trend in the first ionization energies across period 3. Give a reason for the overall upward trend, the discontinuity here, and the discontinuity at P2S, phosphorus to sulfur. Pause the video, process, think how you would answer this. It's really quite simple. We just explain what we've been explaining, okay? So we explain the overall upward trend, and then the reasons for the discontinuities. And there's my long-winded answer there. And I think you should also try to draw the valence shell configurations for the elements concerned, for magnesium and aluminum, and for phosphorus and sulfur, to explain these discontinuities. Okay, I'm not going to walk through this because we've talked about it, but if you want, you can pause the video and write it down. Let's move to another possible exam question. It says the diagram shows the first ionization energies of 5 consecutive elements in period 3. Which element is silicon? Pause the video. Think how you would try to answer this. In 3 seconds, I will show you a clue. Here's a clue. Again, pause and think. So what's the answer? The answer is going to be B. B is silicon. Why? Well, we can see it goes up 3 and then down. So there seems to be a downward tick between C and D. How many times does it go downwards across period 2, across a period? We know it goes downwards twice, between group 2 and 13, and also between groups 15 and groups 15 and 16 here. Okay, so which one is this? Which one is that downward one? We can see it has 3 atoms before the downward tick, which means it can't be this one because here we only have 2 atoms before the downward tick. So this jagged line there must reference this, which means that we're dealing here for B with silicon. Okay. One more thing which I almost forgot to say is that the ionization energy data is in your data booklet in section 8. So at the top left of these boxes, you can grab the first ionization energy for each element in kilojoules per mole. So there might be some questions that would require that you know where to find this information. Importantly, the one for hydrogen is wrong. So they probably won't ask you questions about that because they're off by at least an order of magnitude there. Okay, I think now we have covered the main 3 objectives, and you might need to watch this a few times because some of the explanations I know are a bit wordy. But if you take good notes and you try out the questions on the website, then you should come out in flying colors. Okay, I will see you then in the next video, and until then, stay practicing.